Okay, so if you recall, we have already talked a bunch about type 1 and type 2 errors, specifically in the first section of chapter 9. I remember I gave you that very unique jury scenario, which, was kind of tough to think about how type 1 and type 2 errors would, how they would affect each other. Just remember that they are inversely related. So if you're increasing one, you're decreasing the other, and obviously this causes some issues when it comes to running tests. So if you recall, the probability of making a type 1 error was actually alpha. Also remember that type 1 errors are rejecting a true null hypothesis. So essentially, in every test that we get, we're given a significance level, which is alpha, and we automatically will know what the type 1 error is in terms of probability. But the type 2 error, which is represented logically by beta, we actually don't know. Remember, a type 2 error is failing to reject a false null hypothesis or accepting a false null hypothesis. So far, we've only known that beta is inversely related to alpha, but we've had no way to calculate it. So now that is going to be the key part of this. So I'm just going to read this because this is a very important part of what I printed out here. So it says, conceptually, there are two parts to understanding the process of type 2 probabilities. First, by definition of type 2 error, we are indeed accepting the null hypothesis. Therefore, this requires we locate the acceptance regions for a hypothesis test. Okay, so this is weird. Why? Because we're always sort of fixated on finding rejection regions. So for this scenario, we are going to need to find acceptance regions as well. Next, second, again by the definition of type 2 error, the null hypothesis will be indeed false. So it says, therefore, computations cannot occur based on a normal curve with a given population mean, but rather we're going to be given a new alternative mean. So this is not alternative hypothesis. This is a new mean which actually is true. So this sounds kind of weird, but in general, if we know we're accepting a false null hypothesis, if the null hypothesis is false, we can't use the actual mean that was provided originally in the problem in order to calculate the probability. We need an alternative one. So that's what's actually going to happen in the problems. Now, the process is much different than what you're used to, so this is somewhat of a more challenging topic, but don't worry about assumptions for now. We're going to concentrate just on the probabilities. Also, we're going to concentrate just on using z for these. I'm not going to give you any values with t, so that'll make it a little bit more streamlined, but essentially the process is all about two steps. And these two steps, while somewhat familiar, will also be a little strange to you. So the first part is we're going to be finding what's called x-bar critical values. Now you're used to finding the z critical values. So now we're going to be finding whatever the value is for x-bar. That would be the rejection versus non-rejection location and for the original null hypothesis. Very complicated to say, but you'll see in the example how we're going to do that in terms of the problems. The second step, when we actually calculate the type 2 error, is we're going to have to find the area in the acceptance region for that critical value that you calculated based on the new mean. That is going to be the process altogether. And yes, it depends on whether it's left, right, or two-tailed. And a lot of what I said might have been very complicated to listen to. So why don't we just get into simply doing an example so that we can sort of get through and understand the process. Okay, so it looks like number one, it says, suppose that the manufacturer of a new model car, the Orion, claims that a typical car gets 26 miles per gallon. A consumer advocacy group is skeptical of the claim and thinks the mean gas mileage of all Orions may be less than 26. The group plans to perform the following hypothesis test. Okay, just like they have here, I will be providing the null and alternative hypothesis in any probability of type 2 error calculations. The calculations are difficult enough, So I will sort of give that to you to make sure that there aren't any issues from that standpoint. So what does this all have to do? So the first thing of importance is we need to find what's called the X bar critical value. Okay, specifically for a left-tailed test. Okay, so if you return to just sort of the setup, it said right here, this is the left-tailed test. So what is that formula? It's mu minus z sub alpha sigma over root n. So we're just going to rewrite that down here. So mu sub 0 minus z sub alpha. Remember, if we look at our problem, our significance level is 5%. So we're going to do 0.05. And we're going to multiply by sigma over root n. Okay, so just to be clear, this mu sub 0 is the original mean. That value is going to be the value that is in the null and alternative hypothesis. So what we're going to do basically, calculations-wise, is we're going to get 26 minus, then we have to look up z sub 0.05. Now, I know this is a z value, but remember, this is in the same process as if you were to do a confidence interval. So you're actually still looking in the t-table, but you're looking at the bottom of the t-table at z.05, which is 1.645. So if you get 1.645, it looks like 1.4 is the standard population standard deviation, and then we had 30 cars. Okay, this is going to give us a approximate X bar critical value of 25.6. Okay, so what does this mean? So if I'm not going to write on the graph that's given, I'm just going to write this underneath here. So what is this value? So normally what we do is we find the z critical value and we mark it on the graph as if the mean is 0. So now we're going to take our mean, our original mean of 26, our mu 0, and we're going to put 25.6, which is our X bar critical value, on the graph. So in the original distribution, this is essentially marking where you would have rejected H0 versus not rejecting H0. Do not reject H0. Okay, so we haven't done this. We've only used Z's to mark this, but this would essentially be any miles per gallon that's less than 25.6 mpgs would have rejected the null hypothesis. So essentially what we need to do is this, we need to take this 25.6 and we need to remove it from our 26 miles per gallon. Why? Well, the probability of a type 2 error is accepting a false null hypothesis, which means our null hypothesis is indeed false and we need to be provided an alternative mean. So if you look at this, it says find the probability that making a type 2 error if the true mean Gauss mileage of all orients is actually 25.8. So we now in our new curve have an alternative mean of 25.8. Okay, so we want to take our value here, our 25.6, and we want to place it on our new distribution. Okay, 25.6. So what, again, false mean 25.8, right? False mean. This is the new alternative mean, and we have our X bar critical value. What is the probability of a type 2 error? It's the probability of accepting a false null hypothesis. We want to know in this setting right here, what's the probability of accepting this hypothesis, this false null hypothesis? So if we look at this graph, we know that reject again is over here, and do not reject is over here. So what's the probability of rejecting? That's over here. Therefore, the probability of accepting is actually on the other side, over here. So in order to calculate this type 2 error, we need to find this area right here, which is going to be beta. So how do we do that? Well, we find the probability that X bar is essentially greater than 25.6 in the setting. That is our goal. Now, do we always say it that way? No, but that is what we need to find. How do we do that? Well, the first things first. We need to essentially standardize 25.6 in the setting. So how do we do that? We need to find essentially what the test statistic would be. So we're going to let z be equal to, again, our usual x bar minus mu, except it's going to be the alternative, sigma over root n. Now note, we're doing z-test stuff here, so we're not actually using t's, so we're in the z variable. So what are we going to do? We're going to do 25.6, which is our new x bar critical value. We're going to subtract our new alternative mean, essentially standardizing. And 1.4 divided by root 30 again will give us a approximate value of negative 0.77. So essentially by standardizing this z is 0, this z is negative 0.77. So we need to find the area above negative 0.77, and we will have the result of our problem. So how do we do that? Well, the probability of z being greater than negative 0.77, that is actually just found by either using the z table or using normal PDF. So if we use the z table, we're looking up negative 0.77. So that's going to put us about, so we're in this column here. So that's going to put us at about here, 22.06. So if you go back to here, remember 22.06 is the value that is below negative 0.77. So we have to do 1 minus our 0.2206. And that is going to give us approximately 0.7794. Okay, so this is going to be our value of beta, which is the probability of a type 2 error. Okay, there's an important thing to note here. So you'll see obviously in this problem that we had an alternative mean of 25.8. In reality, if we're accepting a false null hypothesis, the alternative mean that's provided to you could be any value. So it turns out that you could end up doing a whole nother problem by finding the probability of a type 2 error based on, let's say, a new mean. So if you're looking at this right now, this is saying find this unique type 2 error probability, returning to number 1, same problem, right? But they're saying do it as if the alternative mean was 25.3. So it should make sense to you that the type 2 error probability is going to change if there's another mean, because think about it. Let's say our new mean is 25.3. So this is our alternative mean. So our x bar critical value is not going to change no matter what we do in this left-tailed test. These values here, this 26 right here doesn't change. Z sub 0.05, our alpha is still 0.05, and sigma and root n don't change. So we're still, in this scenario, going to get 25.6 as our x bar critical value is 25.6. So that's not going to change. But what is going to change? That 25.6 was to the left of the mean right here. Now, if we look at our new alternative mean, the 25.6 is now on this side, right? But this is where it gets a little complicated. So this is a left-tailed test, believe it or not. I know that sounds weird, but this is still a left-tailed test. So the rejection region is still over here, and the acceptance region is still over here, which means in order to find this type 2 error, beta is going to be still on this side. So this is a little complicated. I know most students are going to be used to seeing a tail that is small and think that that is the rejection region, which is logical. But in this scenario, we're still at a left-tailed test, so we're still with an acceptance region on this side. So how do we do something like that? Well, we're basically following the same process as over here, but we're doing it as if we have a new mean of not 25.8, but 25.3. So we're essentially copying that entire process. So what do? We find our z again, which is going to be 25.6, but this time minus 25.3 over 1.4 divided by root 30. This is going to give us a z value of 1.15. So now this is indeed 0, this is as it always is, and this becomes 1.15. So we're trying to find the area, again, greater than, z greater than 1.15. But in order to do that, we have to find 1.15 in the chart and subtract from 1. So if we go into the chart, we have to go into the other side here. If we go to 0.05, let's just make sure, oh, we're good here. So 1.15 is 0.8749. So 0.8749. So if we do the subtraction there, we're going to get 0.1251. And you'll see that if you look at the areas that we calculated, the probability of a type 2 error has actually decreased significantly with this new alternative mean, or in other words, the probability of accepting a false null hypothesis has decreased significantly. So just to all right, let's continue on to the last concept in this section. I'm just going to read. It is very common for statisticians to measure the performance quality of a hypothesis test by its ability to not make a type 2 error, namely, making the correct decision and rejecting a false null hypothesis. So realize that a type 2 error is accepting a false null hypothesis. So now a correct decision, logically, would be rejecting that false null hypothesis. And in reality, that's what hypothesis tests are made for. They are created to challenge the null, and they would like to reject it in general. But moving on, it says the probability of not making a type 2 error is commonly referred to as the power of hypothesis test. Okay, nicely enough from this definition, the power of a hypothesis test is simply 1 minus the probability of a type 2 error. This is obviously a very simple calculation and pretty much something we can handle, right? So for number 3, it just says return to number 1 and 2 and find the power for each test. Remember, we were dealing with the Orions, one with an alternative mean of 25.8 and one with an alternative mean of 25.3. So now we're going to find the power in both these scenarios. So let's do that. So let's say for when the alternate mean was 25.8, the power is going to be equal to 1 minus beta. Okay, beta in that scenario, if you recall, was 0.7794. A little bit of calculator work, and you're going to get 0.2206. What if the alternate mean was 25.3, which was our other example? That'll end up being 0.1251. So power equals 1 minus beta, or 1 minus 0.1251, which is 0.8749. Okay, so these are the probabilities of rejecting, properly rejecting a false null hypothesis, i.e. making the correct decision in these tests. So a lot of times, statisticians will look at the power of a test in terms to grade its quality. So if you look at this little chart right here, it's not technically ideal just to do 2 random alternative means. So if you can see real quick, if you look at the true means column right here of this, we have already calculated 25.3 and 25.8. So you can see right now that our probabilities that we have calculated are here. These are the problems we did, and here, right? But it would be ideal to have all of the alternative means to check to see how the power of this test is basically behaving. We, of course, are not going to go through and calculate all these, so I brought them in as an easy little look at what the power is going to do. So this is a good way to look at the power. So reading along right over here, It says, hopefully the clearest observations to be made here are as the alternative mean gets farther away from the original mean, 26. Okay, so 26 is down here. So it's saying as it gets away from the original mean 26, what happens to the power? Well, it looks like the power is increasing in value. So power will increase, and then it seems to be approaching what value? Or in other words, if you were in calculus, what limit is it approaching? Well, it seems to be approaching a probability of 1. Okay, so we can also make a power curve. So what is a power curve? It's basically just plotting the values over here in our little chart here. So if you look at the true means are at the bottom, alternative means are down here, our UAs, and then our probabilities are over here. So all we did was plot the first and the third columns of our chart over here. So we have that curve. So reading below, it says the most ideal power curve is one where the beginning of the curve stays near a power of 1 as long as possible before sloping down. One way to achieve this is to increase the sample size used for their hypothesis test. Okay, so if you look at this scenario, first things first, why is it ideal for this to stay as close to 1 as much as possible? Because that means that the power of the test near its end is going to be very good at rejecting a false null hypothesis. If it falls away from 1 quickly here, then it's not going to be as good as long as possible. So we want it to be that. So what I did basically was I took our original graph again, this over here, our little original table, and I copied the graph. So the graph is actually right here. But then I brought in the same calculations with an n, a sample size of 100 instead, and then graphed it. If you can see, as I increase the sample size, the power of the test actually remained closer to 1 as much as possible. So it's sort of flattened at the top. So this is the most ideal scenario in this case. So it says, hopefully you see that the power reached 1 very quickly as the alternative means got farther away from 26. This ultimately shows us that the hypothesis test will be more effective at rejecting a false null hypothesis with n equal to 100 than n is equal to 30. So the key is, again, increasing the power of the hypothesis test is all about increasing the sample size. Okay, so let's do an example problem using power. Note that we are not going to be calculating power directly, but we're going to need to calculate the probability of type 2 error in this setting in order to eventually get the power. So let's read the problem. It says, suppose the building specs in a certain city require the average breaking strength of a sewer pipe to be more than 2,400 pounds per linear foot. Each manufacturer who wants to sell such pipe in the city must demonstrate that its products meet specifications. Okay, so specifications are basically the alternative hypothesis, which is more than 2,400 pounds per linear foot. We are going to be doing this at the 1% significance level, so that is our alpha, and a sample of 50 sewer pipes. Okay, it says assume the breaking strength of the sewer pipe are normally distributed with sigma equal to 200. Our goal is to find the type 2 error probability and the power if the alternative mean is 2450. Okay, so just as a reminder, so now we need to find the x bar critical value, but we're doing it for a right-tailed test. So how is that going to change? Last time we did a left-tailed test, so when we did the formula we had to subtract. Now we're going to have to add. So basically, we're doing the original mean, our 2,400, but now we're going to add our z sub alpha and multiply by sigma over root n. Just note that alpha is 0.01 in this problem. So if we do that, we have 2,400, which is our mu naught. We're going to add z sub 0.01. So if we go to z sub 0.01, that's right here. So we're taking 2.326. and we're multiplying by our sigma 200 over the square root of our 50 pipes. If we do so, we're going to get an approximate X bar critical value of 2465.8. Okay, so remember, this marks essentially in the original distribution where the cutoff is between a value, a pound per linear foot measurement of whether the hypothesis would be, null hypothesis would be rejected or not rejected. But for the purposes of our test, we don't want to know what that is. We want to know what it is in terms of the alternative mean. So if you draw a little curve here, it says that our alternative mean is 2450. So we're going to put our 2450 alternative mean in the middle, and then we're going to plot our 2465.8, which is going to go, we're just going to make an approximate value here of 2465.8 right here, which is X bar. Okay, so in this setting, this is where that value falls. Now, remember, again, type 2 error is the probability of accepting a false null hypothesis. So we know that it's false, but we need acceptance. So normally in this setting, we would say that rejection is going to be in the tail, right? So in any test, we always are talking about rejection. So that means that acceptance is actually going to be on the other side. So remember, this is a greater than test, right? So if it's a greater than test, then our rejection region is on this side, reject, right? But we want do not reject over on the other side. So in this standpoint, in order to find the probability, we're looking for the probability that our value of X bar is actually less than 2465.8 in the setting where the alternative mean is 2450. So what do? Well, we have to standardize, right? So our typical calculations are, let's get our Z value. So our Z value is going to be 2465.8 minus our 2450, our new alternate mean, divided by our 200 divided by root 50. This is going to give us a Z-score of 0.56. Okay, so remember, this is basically 0 is 0 now. This is 0 is 0. Z is equal to 0.56. So we're looking for the probability, which is this is equivalent to the probability that Z is less than 0.56. So what do? We simply just look that up in the Z table. Now, luckily, unlike last time, all we have to do is look up that value and we're going to get what we need. So if we go to 0.56, give me a second, hit the wrong thing. Okay, if you go to 0.56, then it looks like we're going to get 0.7123 as our value. So we're going to head back. This is going to be this area over here. It's going to be 0.7123. That is also this area right here. So this is essentially beta in our problem. Okay, so that's the probability of selecting a type 2 error. So therefore, the power is going to be equal to 1 minus 0.7123, which is going to give us 0.2877. Okay, and those are our two results for our problem. A small note for number 5, we're not going to be covering a two-tailed test in this setting, so don't worry about that.